In this video I'm going to talk about two special types of production functions. The first one is called perfect substitutes. With perfect substitutes, the rate at which capital and labor can be substituted for each other is the same no matter what level of inputs is being used. In other words, the marginal rate of technical substitution is constant. It doesn't matter as we move along the isoquant, the rate at which we can replace capital by using labor is going to remain constant. Let me give you the general functional form of this type of production process. This is going to be the general functional form for perfect substitutes. The marginal product of labor is simply going to be A, which is technically the partial derivative of this equation. The marginal product of capital will equal B, which is the partial derivative of this equation with respect to capital. A graph of the isoquant when we're dealing with perfect substitutes is going to be a downward sloping straight line. Okay, so this is going to be the isoquant. So let's do an example. Let's say the production process is characterized by this idea of perfect substitutes. We have something like this. If we were to graph an isoquant for this, say when Q equals 100, we could then graph the isoquant. So one way to produce 100 units of output is just use nothing but capital. So if L equals 0 and K equals 10, plugging that into this above equation, we're going to get 100 units of output. Alternatively, if K equals 0, we can produce 100 units of output by using 20 units of labor. 5 times 20 gives us 100, and K is 0. So our isoquant looks like this for 100 units of output. So here again, the slope, the marginal rate of technical substitution, which is the absolute value of the slope, it doesn't change. So the marginal rate of technical substitution in this case is 1/2. In other words, 2 workers can replace 1 unit of capital. And it doesn't matter if we're starting at 10 units of capital, 5 units of capital, 3 units of capital. It'll always be the case that 2 workers will replace 1 unit of capital. So that's the idea of perfect substitutes. So let's do maybe a mathematical example where we're trying to find the optimal input mix. So here's another perfect substitutes type production function. Let's say 8. Okay, and let's say that the firm is interested in producing 20 units of output. Okay, that's the firm's profit maximizing output. What is the optimal input mix? We need to calculate 2 ratios and compare them. We're looking at the marginal product of labor divided by the wage. Okay, this is just the additional output obtained by spending $1 more on labor. It's a bang for the buck measurement. In this case, the marginal product of labor is 2. The wage is 10, so this is 1/5. By spending $1 more on labor, our output goes up by 1/5 of a unit, or 0.2. The marginal product of capital divided by the price of capital, if we do that, the marginal product of capital is 1, which is the coefficient on K, divided by 1/8. So in this case, if we spend $1 more on capital, our output only goes up by 1/8 of a unit, or 0.125. So it appears that we're getting more value for our money by hiring labor. We're getting more output per dollar. So in this case, we should just hire all labor. So we're going to hire all labor to produce our optimal input mix. So we're going to hire all units of labor and no capital. So how many units of labor are we going to hire? Well, if we're going to produce 20 units of output, and we're not, let me just rewrite this. If we're going to produce 20 units of output, and we're not going to hire any labor, in other words, K is 0, well, we're just solving for this, and L equals 10. And K equals 0. So that is our optimal input mix, and how to solve it when you're dealing with perfect substitutes. Again, calculate those bang for the buck measurements, the marginal product divided by the respective price for that input, and find which one is giving you the most output for your money. Alright, let's do one other special type of production function. This is going to be perfect complements, or sometimes called fixed proportions. In this type of production process, only one combination of labor and capital can be used to produce each level of output. So again, it only makes sense to only use one particular combination of labor and capital to produce a particular level of output. So in terms of substitutability between inputs, there isn't any here. There's only one input mix that makes sense. So for example, let's look at this first graphically. So we're in the taxi cab business. We got cabs and drivers. Isoquant is going to look something like this. Here, if you want to produce an output of 1, or Q equals 1, it makes sense to hire 1 driver and 1 cab. Any other combination is not going to be useful here. Having 2 cabs and 1 driver, that's not going to be able to produce you more output. Alright, you need to use these inputs in this fixed proportion. Likewise, having 1 cab and 2 drivers, you're still along the same isoquant. You're not going to be able to produce more output. So in this case, it only makes sense to be here at the elbow or the kink. We could get on a higher isoquant. Here, to get our output at 2, requires 2 cabs and 2 drivers. So the production function I'm describing here is taking on this following form. Output is going to be the minimum of what's in parentheses here. Okay, output is going to be the minimum of what's in parentheses here. So describing what I have in the diagram, the production function would just simply look like this. The minimum of L or K. So if we plug 1 and 1 into the production function, okay, the minimum of 1 and 1 is just 1. Our output is 1. If we plug 2 and 2 into the production function, the minimum of 2 and 2 is 2. But notice this, if we have one cab driver and two cabs, we're not going to produce any more output. The minimum of 1 and 2 is 1. Okay? So one cab and two drivers, we're still on the same isoquant associated with 1 unit of output. Two cab drivers and one cab, that's not going to get us any more output than 1 and 1. So we're still producing 1 unit of output. Alright, so let's try to find the optimal input mix in this environment. Let me do a problem. So let's say we want to produce 50 units of output. Okay, let's find the optimal input mix to do that. So the way to do that is to take what's in parentheses. Okay. So we just got L and K here, so I'm going to set it equal to each other, and then I'm going to set it equal to 50. So in this case, we're going to hire 50 workers and 50 units of capital. That is the most efficient way of producing 50 units of output. And of course a minimum of 50 and 50 is just 50. We get our 50 units of output. Okay. Notice here I didn't have to take into account the wages, okay, of labor or the price of capital. Okay, so this is how you solve these problems. Let's do another example. Just tweak the production function slightly. Oops, sorry. Put the L over here, doesn't matter. Okay, so let's try to find the optimal input mix once again when we're producing 50 units of labor. So in this case we're going to take what's in parentheses, set it equal to each other. L equals 2K. You're going to set that equal to 50. So in this case L equals 50, 2K equals 50, or K equals 25. Okay, so the optimal input mix here requires that the firm use twice as much labor as capital. So L is 50, K is 25. And I'm just illustrating this. I just want to point out that with perfect substitutes, the optimal input mix doesn't always have to be 1-to-1. Okay, the optimal input mix could be hiring twice as much input over the other, like in this last example.